Okay, please let me know if everyone can see the screen. Okay, very good. Okay, before this, in our previous class, we saw how we can apply force method for frames and also beams. But as I said, mostly force method is used for trusses because it can make our calculation much faster than other techniques that we know. And as I said, in the final exam, almost always you have one question from truss on indeterminate truss. I'm not going through the explanation again for determinate, indeterminate. It is in the video that I have already uploaded, so you can watch it. Today, we just focus on two examples to see how force method can be applied for trusses. Okay, what you see here is one of that example. I will enlarge the screen, okay. Here you can see we have a truss, and the truss is subjected to force 60 ton. The dimension of the truss has been given to us, 9 meter and 12 meter. And these values that you see on the P elements, these are the cross-section area of each element, 75, 60, 60, and 75. And the modulus of plasticity is similar for all the structural elements. Now, the question is how we can analyze these truss using force method. Okay, like beam and frames, the first thing that we need to do is to determine the degree of indeterminacy. For this truss, if you look carefully, you can see we have 4 supports, 2 roller supports, and 1 pin support. So each roller support gives us basically 1 support reaction, and the pin support is giving us 2 support reactions. So totally 4 support reactions. We said we can write down 3 equations that are indeterminate. So therefore, 4 minus 3 equals to 1, meaning this truss is externally 1 degree indeterminate. Now that we know that truss is not determinate, we cannot use the normal techniques like the joint techniques that you can cut and analyze one joint by joint. And we need to use the force method to analyze these truss because it is indeterminate. Okay, how we can do that? Like beam and frames, we need to basically select the redundant support reaction. You remember when it came to the beam and frames, I said one of the criteria is that if you select any of the support reaction as an indeterminate support reaction, redundant support reaction, you need to make sure that your truss is going to be stable after you remove that support reaction. For example, in this case, we have pin support here. If you consider the horizontal reaction of these pin support to be redundant, then the truss is going to turn to a truss with 3 roller support. Because if you remove that one, the pin turns to a roller. So if you have 3 roller support and you have a horizontal force, your truss is going to move to the right side, which makes it unstable. Therefore, horizontal support reaction of this pin support cannot be selected to be as a redundant support reaction. But any of vertical support reactions, you can select it to be the redundant one. So for this example, we have selected the vertical support reaction at point B, as you can see, and we show that one as XP. So the moment that you know this XP, basically your truss is going to be a determinate truss, and you can start using the joint techniques, meaning you can separate this joint and by sigma phi equals to 0, sigma fx equals to 0, get the forces and joint by joint until you reach to the head. So right now, our main intention is to calculate this XP, because if we calculate that one, our truss can be analyzed by normal techniques. So similar to beams and frames, in order to get this XP, we are going to have 2 structures that basically combination of these 2 can represent the real truss that we have. In this structure, basically one of them is going to be exactly similar to the first structure with the external force that have been applied there. But of course, we don't have the support reaction. We have removed it. In that case, this truss become a determinate. However, since we have removed the support reaction, the problem is that in that joint, we are going to have some deflection. While in the reality, because of the existence of this roller support, the deflection there was 0. So in order to deal with that, we are going to have another structure that this second structure doesn't have the external force, but instead it has a force applied to point B that wants to bring back basically that deflection. We don't know the direction of that deflection in reality. It is toward up or down. It doesn't matter. We can assume it to be in any direction. What matters is that the force that you apply here should make that deflection such that to be equal to the deflection that occurs in this structure. This way, if delta BB equals to delta B0, these two can represent the real truss because it has basically the 64 there, the structural elements are all the same, and then our force also is going to be equal to this XP. So in order to make these two truss similar to these, meaning these two truss combination of these two truss become a representative of the main truss, we can write down the equilibrium equation and the compatibility equation or condition, which says that delta B0 plus XP multiplied by delta B should be equal to 0 because there is no deflection. And then we said why we use XP multiplied by delta B, because we don't know exactly how much force we should apply here to make delta BB equals to delta B0. But we know if this force is basically exactly calculated, it should be equal to this XP. So that's why we apply XP multiplied by delta BB. So in this case, right now, in order to get that XP that makes our truss determinate truss, you can see we need to calculate two deflections, delta B0 from the first structure and delta BB from the second structure, right? So how we can calculate this deflection? If you remember from our first class, we had an equation for truss through virtual work method. We said if you want to calculate the deflection inside the truss similar to this one, you need to have a second truss. In that second truss, you're going to apply a unit load to the location that you want to calculate its deflection, which is going to look like this truss actually. So if you remove this one and apply a force here, you have this truss. So from this truss, you can get the force F, and from the second truss, you can get the force F bar, and then you can put it inside our equation and get delta B0. So F is the internal force of the structural elements in the first truss. F bar is the internal force of the structural element in the second truss. That the second truss doesn't have the external force, but it has a unit load applied to the location of interest. And then you need to multiply that one to the length of element divided by the cross-section area multiplied by the modulus of elasticity. So one by one, you need to do this, meaning you need to multiply this force to the length of this element divided by EI, then go to the second one until you reach to the last element and sum it up and get the delta B0. For the second structure, again, we need to calculate this delta BB. So if you want to generate the second truss to calculate delta BB, you will see that since this truss doesn't have any external force, if you remove this one and you apply the force exactly to the same location, the F and F bar basically is going to be similar because the trusses are going to be similar. Therefore, the equation for the calculation of delta BB is going to change to this equation, meaning F and F bar become similar. So whatever you get from the first truss, power 2 multiplied by L over is going to give you the delta BB. So this is what we are going to do. So right now we have two trusses. From the first truss we get F, from the second truss we get F bar. Then we are going to put it inside these two equations and get delta B0 and delta BB, and then calculate the XP. The moment that we know the XP, we can start analyzing our truss. So this is what we have done here. You can see the first truss, which is a determinate truss, have been analyzed. So if you want to analyze this truss, first you need to get the support reaction, and then joint by joint calculate the internal forces. Don't forget that if you have tension inside your element, the value is positive. If you have compression, the value becomes negative. So this is going to give us F under the 60 ton. And for the second truss, we have only 1 ton force here, which has been applied, and then the support reaction and the internal forces. So this is going to be F bar, and this is going to be F. So if you want to calculate delta B0, F and F bar should be multiplied, meaning 50 multiplied by 0.6 multiplied by its length divided by EI. Then go to the second element, negative 50 multiplied by 0.6 multiplied by L, the length, and divided by EI until you reach to N. So you can see the calculation is going to be very long if you have many structural elements one by one. So that's why normally we make a table in order to do the calculation of delta V0 and delta VB. This is what we have done in our next slide. So you can see in this table, in order to calculate delta V0 and delta VB, we have different columns. The first column is the name of elements, A, B, B, C, then the length of element, then the cross-sectional area, and then we have calculated L over A because this is part of our equation for calculation of displacement. Then you can see the F that comes from the first truss, F bar comes from the second truss. For each element, you just need to extract from the calculation that how much is F and F bar. And finally, we go to the equation that we have, F multiplied by F bar, L over A, F bar power 2, L over A. You can see the E is missing here in our equation. Basically, we have this E over there in order to calculate delta P and delta V0. But here we haven't put that one. The reason is that actually E is similar for all structural elements. So you can do the calculation and then at the end divide it by E. So that's why we haven't put the AE over there. So right now that you have F bar L over A and F bar power 2 L over A for all elements, you need to just sum up because we have that sigma in our equation. So you sum this one plus this one plus this one, you get this, and similarly for F bar. So if you divide this value to E, as we have done here, you get delta V0. If you divide this value to E, you get delta VB. So the moment that you get delta V0 and delta VB, we can put it inside our compatibility equation, and then you get XP. So you can see here the XP become negative. The moment that it become negative, that means that the basically direction of this support reaction in an opposite direction of the force that we have applied here. So XP should be toward down. That's the basically result of this study. Meaning, if you want to calculate the other support reaction, you should put here 8.7 toward down, and then you can calculate the other support reactions. Okay. So now that we know the XP, one way to get the internal forces is to calculate the other support reaction and then use the joint method. So joint by joint, you can analyze. But there is another technique that can make our calculation much simple. So this technique uses one equation to calculate the internal forces. So if you want to calculate the internal forces directly without going through that joint by joint technique, you can use this equation. So if you want to know how much is the internal force of AB in the real structure, is going to be F bar multiplied by the XP that we have calculated plus F. So for this element, for example, AB, F bar is negative 0.375, so you should multiply this one to negative 8.4, and then plus the value of F, which is negative 30. So it gives you negative 26.8. So this is the internal force of AB in the real structure, the first structure that we wanted to analyze. We can do that one by one for each structure element. So you can get all the internal forces without going through the joint by joint calculation, which is very fast and is good for your final exam when you don't have enough time. So you just remember this equation, F bar multiplied by X plus F can give you the internal forces of real structure, real trusses. So after you got these internal forces, you can calculate the support reactions as well. Often I can see in the final exam, you stop here without calculating the support reactions. In the exam, normally we ask you that how much is the support reaction in the real truss, but that table gives you only the internal forces. Still, you haven't calculated the support reaction, so you lose marks. So after you got all these internal forces and you know how much is the unknown support reaction, the other two has to be calculated by a calculation, and you get the mark for that part as well. Okay, so this one was for the truss that is selected the external support reaction to be redundant. But in trusses, actually, it is not always that we select the external support to be a redundant structural element. Sometimes the internal structure element can be assumed to be the redundant one. So this might be the question in the final exam of the test too. So one of these two cases may occur. Maybe we ask you the support reaction to be redundant, or we may ask you one of the internal element to be the redundant one. So this is the example for the case that internal element can be considered to be redundant. So what you see in the left side here is a truss which is given to us to be analyzed through force method. So you can see the length is 90 centimeter, height 120, and a 10-ton force has been applied to point A. So if you check on this truss, again, you can see that we have two basically pin support. So give us 4 support reactions. Then our structure is going to be 1 degree indeterminate. Now, if you want to analyze this truss through the joint technique, you cannot because the truss is indeterminate. So you need to use the force method. The question says, instead of taking the support reaction to be redundant, assume that element AC is redundant. Okay? So when we say element AC is redundant, we mean that you need to remove the element AC from your structure and calculate how much is going to be the force inside these elements. Of course, if you know the force in AC, then you can use the joint technique to calculate the other elements. So if you know this one, the other two can be calculated by writing sigma of y equals to 0, sigma of x equals to 0 and point A. And then after that, you can get the other element. So our job right now is to calculate how much is the internal force in AC. So in order to do that, similar to what we did for support reaction, we are going to remove the internal force in this element and represent it by force like X. So if we calculate how much is this X, basically our structure become determinate one because we know how much is this X. So we can calculate AD, we can calculate AB by writing sigma of y equals to 0 and sigma of x equals to 0. Now, in order to get this value of X, again, we are going to have two structures, similar to the previous case. That combination of these two is going to represent the real structure. So what are these two structures? The first one is a structure that doesn't have this element. Similar to the one that you can see here, but it's going to have the external force that we have applied to the real structure. But the problem is this structure alone cannot represent the real structure because the moment that you remove this element, you are going to have a displacement of delta A that wants to make C and A coming closer to each other, or getting distance from each other. So in order to deal with that, we need to have another structure, another truss, that we can apply a force along the element AC. Don't forget that the direction of this force is not vertical or horizontal. It's always along the element that you remove. So if your element is diagonal, it's going to be diagonal. If it is vertical, it's going to be vertical. If it is horizontal, it's going to be horizontal. So we are going to have another force applied to point A and point C. So don't forget here also the force is going to be applied in both joints and the intensity of 1. So these basically two forces are going to push back the truss such that the deflection at point A and C along the diagonal direction is going to become 0, or the value that exists in the real structure. So right now we are going to have two trusses. That combination of these two trusses is going to represent the real structure. How it can happen? Only when delta A equals to delta AA. So similar to what we said for the support reaction case, if delta A and delta AA are similar, then these two structures can represent the real structure. So in order to make these two represent the real structure, again, we can write down the compatibility condition, which is exactly similar to previous case. Meaning this delta A plus X multiplied by delta AA should be 0. Why we put X here? Because we don't know how much is exactly the force that we need to apply to make the deflection equal to delta A. So we just assume to be unit, and if we estimate that basically correctly, so it's going to be the value of X. So this is going to be our compatibility equation, and as you can see, again, we need to calculate two parameters, delta A from the first structure and delta AA from the second structure. So the equation that we have is similar to the previous case. If you want to calculate delta A according to virtual work method, you need to have a new structure similar to the first one. that we have two unit load applied to point A and C. So if you look, it can be exactly similar to this structure. We remove the external force. Instead, we apply two unit force in point A and point C. So from this structure, you get F. From this structure, you get F bar. And then you can put it inside this equation. You can calculate this delta A. So don't forget, always the force is along the direction of interest. Now, if you want to calculate delta AA, again, we need to have another structure similar to this one. You need to remove the external force, but apply a unit force in that location. So you can see, if you do that, the second structure is going to be exactly like the first one. That's why F and F bar will be similar. And our equation is going to turn to F bar power 2, meaning whatever is internal force here, you power 2 multiplied by length divided by AE, sum it up, it can give you the delta AA. So we need to analyze two trusses. One truss is this one, we get F. Second truss is this one, we get F bar. And then we can put it inside our equations in order to calculate delta A and delta AA. So when you get delta A and delta AA, you can calculate this X, the force here, and your structure becomes determinate. So you don't have any problem to analyze it with equilibrium of equation. So this is what we have done. Until this 10 ton, don't forget, this is not any force here. This is just to show you delta A. Okay, this is not one. I have just slashed it here. Sometimes I can see you have put in the exam especially this unit force in both trusses. No, the first truss doesn't have the element, but has only the 10 ton. The second truss doesn't have external force, has only unit force in that location along the direction. Okay, so right now, in order to calculate delta A and delta A, we need to have F and F bar. So from this structure, we get F. So you need to analyze it. So you see there is no element here. The truss become basically determinate truss. You just need to sigma Fy equals to 0, you get this one, sigma F equals to 0, you can get this one. And joint by joint, you can calculate. And from the second truss, you can calculate the value of F bar. So this is what we have done. We have 2 point loads here. You can calculate the support reaction and joint by joint calculate all the internal forces. Now that we have F and F bar, again, similar to the previous case, in order to calculate delta A and delta AA, we can make a table and put this F and F bar inside table together with L and AA. If E is similar for all structural element, which is similar here, so you can actually omit the calculation of E inside your equation. At the end, you can add it. This way, the values are not going to be too much big or too much small in the table. So you can see the table has been generated. This is the structural element, the length of the structural element, the cross-section area. L over A have been put here. And then this is our F for each element from the previous slide. F bar, again, for each element have been placed here. And finally, calculation of the deltas, F multiplied by F bar multiplied by L. So you can just see this multiplied by this, you put it here. It's very easy right now in the table how to calculate. And F bar power 2 multiple L over E. Then you need to sum all of these. Don't forget always, sometimes I can see you can mistake in the sign of the calculations. If positive, negative, you need to take it into account. So at the end, you get the value of F bar LE, and you need to divide it by E because you don't need to put the E there. So this gives you delta A, and the second calculation gives you a delta AA. So you have delta A and delta AA. You put it inside the compatibility condition, you get X. So this X is the internal force. When it is positive, that means the force is in the direction that you have assumed for your unit load. So it is exactly in this direction. It pulls point C, it pulls point A, and it is tensile time. So right now we have calculated force in AC 7.35. Now, if you want to calculate the internal force of other elements, you can use this equation that we have, F bar multiplied by X plus F. So you can multiply this F bar multiplied by 7.3. So negative 0.8 multiplied by 7.3 plus F plus 10, it gives you the internal force of AB. And likewise, you can do the calculation for other structural elements. Okay. And finally, you get all the internal forces. So you get the internal forces, but still you haven't calculated the support reaction. Do not stop here. If we have asked you to calculate the support reaction, do the calculation for support reaction as well to get the full mark. So this was two examples from the Truss that we applied the force method in order to analyze the internal forces. There is one more example I've uploaded inside e-learning. In the video that I have recorded for you, I have explained everything in detail. So it was just a review of that video for today. If you have any question, please ask. Otherwise, we can go to our new technique, which is we are going to learn today about influence line.
Doctor, I have 3 questions actually, if I may ask. Okay, so first of all, when the question asks us to use the member as a redundant, is the question going to tell us which member to use?
Okay, very good. Okay, let me answer the first question. Normally in the exam, we tell you which element should be basically considered to be redundant. But there have been questions in the past semesters that we have asked the students, for example, in this case, we have asked the student that which element can be removed and considered to be the redundant one, and which element cannot. So as I said, the main criteria is if you remove that element from your structure should remain stable. So we have asked you to find which element is basically suitable to be the redundant one. I think only in one semester we had such question, but often we ask you directly to select the element that has basically redundancy. And we can just say, okay, consider the horizontal support reaction at point C to be redundant. But it's not often always occurring this way. Sometimes also we ask you to select it by yourself.
Okay, Doctor. So my second question is about the settlement. When we have a settlement, I know that the equation should be equal to the settlement, but should the value of the settlement be positive or negative?
Okay, that doesn't matter because at the end of the day, if you put positive or negative, what you get is going to be in opposite direction of the force that you have put there, or exactly in the same direction. What is important is that when you have settlement, for example, let's go back to the previous class. Okay, example. Okay, here. Let's say we have settlement at point B. Okay, settlement at point B. So the settlement is always toward downward. Sometimes even if we say it is toward upside, doesn't matter. So you need to consider the direction of your force basically together with its direction of settlement. These two should be in a similar direction if you want to make a calculation. Meaning, if your settlement is toward down, you should consider this force also to be toward down. So that way your value here is going to be a positive value. But if we say point B has 3 centimeter moving toward up, so you put this redundant force toward up. This way, this deflection and that force is going to be in the same direction. And then you can put the value here again, positive value.
So if they were not at the same direction, it should be negative, right? Because I have tried to solve one of the questions and I did not use the same direction, so I had a lot of mistakes at the end.
Yeah, if you don't do that, you may not get this correct result, because I think it was previous semesters. Previous semester we gave equation a test to a question to final exam that the question had settlement. Don't forget, if we say point C has settlement, you must consider point C to be the redundant location for you, and then write down the equilibrium equation for that location. You cannot say point B and then point C has we remove the support at point B, and then you assume that point C has settlement. No, if we say that in this truss, let's say point A has settlement, then you need to know that the redundant support reaction should be point A. Otherwise, we cannot write down the compatibility condition. So let's say point A has 2 centimeter settlement. So in that condition, you remove point A instead of point B, and you put the force toward down, and then you do the calculation. And then that is going to be a positive value in the right side for you.
Okay, Doctor. So my last question is about when we calculate the internal forces in the members, can I in the test just put the value directly, or should I show the X component and Y component?
No, for me, as long as you can got these values correctly, you get the mark. So I don't need you to put here what is X, what is Y. I need only to see whether you have got this 50 correctly or not.
Okay, doctor. Thank you.
Okay. Any other question?
There are questions.
Yes.
In the previous lecture video, you mentioned about internal indeterminate will collapse when one member removed.
Okay.
Can you explain more about that?
Okay, so you're referring to this page, right? That we have instability inside our structure.
Mhm.
Can you repeat your question so that I can understand it well?
I don't understand why when one member is being removed in internal indeterminate structure, it will collapse.
Why we remove? You're talking about truss or you're talking about the frame?
The previous page just now Dr. Shaw.
This one?
The one with a lot of yes, this one.
Okay. So you're talking about these instability, you mean?
Yes, the condition with internal indeterminate.
Okay. Right now, so I need to explain this one. If you have watched the video, you can see that there I have mentioned that the trusses can be internally determinate or internally indeterminate, and externally determinate or externally indeterminate. So this is basically in this page, I have shown to you that how you can understand your truss is internally determinate or indeterminate. Besides determinacy, we have also instability inside the trusses. For example, this equation that we have here shows that whether your truss is basically stable or unstable. Stability means under the load that applies to the structure, it can resist without large deformation. So if your structure is in such a condition that after you apply the load, it can collapse or have a large displacement, so we consider it to be unstable. One example basically is like the one that you see down here, is this truss. As I said, the equation is 2G should be more than M plus R. J is the number of joints that you have here. So we have totally 8 joints. You can see 1, 2, 3, 4, 5, 6, 7, 8. And N is the number of elements. We have here 12 elements, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And if you have watched the video, I've mentioned that R is always equals to 3 for the plane trusses. And so 2G means 2 multiplied by 8 becomes 16. And N plus R is 12 plus 3 is 15. So you can see 2G is larger than N plus R. That means this truss is internally unstable. What does it mean? If you apply a force horizontally or vertically to this truss, you will see that the truss is going to have a large deflection. It comes down. So this truss is not tolerating any force that is applied to it, and it is in an unstable condition. Let me just give you another example. Let me see if I can draw it here. Okay, let's say we have a truss like this one. Here we have 1 pin and 1 joint. So these are our joints. Okay, we want to see whether this truss is stable or not. So again, we can calculate 2J. We have 4 joints. Multiplied by 2 is 8. M, we have 4 elements plus 3 is going to be 7. So 2J become 8. M plus 3 is 7. So you can see again the same condition occurs to this truss. So this truss considered to be unstable because if you apply a force, let's say a horizontal force, to this location, your truss without resisting is going to deform like this and is going to collapse. However, the other truss that you can see here that has one diagonal element, The moment that you apply the force, is going to resist, because this force is the element is going to tolerate the force that comes horizontally to the truss. So what we say about instability that leads to collapse is similar to this case. That means your truss cannot tolerate the force, and is going to show a large deflection inside structural elements. And finally, if the force is too much big, it's going to collapse. So did you got what we mean by this one, unstable?
Doctor, what
Yes.
if the structure is indeterminate internally? Does the structure still stable? Is the
Yes.
structure still?
Yes, if your structure is internally determinate, definitely is going to be stable. There is no problem. But I can give you another example that your structure become unstable, although internally. Okay, so if I put here one roller here and one roller here, and I apply a force to this, if you calculate, you will see that the structure is internally indeterminate, meaning it has more than whatever it needs. But since you have two rollers that cannot take any horizontal force, if you apply the force, your truss is going to move to the right side. So since this truss is externally basically unstable, so the truss is still considered to be unstable truss. So you need to check on the external and internal condition. Internal condition is very clear. You use 2J should be larger than M plus R, so you become unstable. And for external, you need to have at least 3 support reactions. In this case, we have only 2 support reactions. So meaning one support reaction is missing to tolerate the horizontal force and make the truss to be also unstable and can lead to movement to the right or left.
So does that mean if the structure is indeterminate internally, the structure has the possibility to be stable or unstable?
Yes. You need to check on the external condition. If externally is determinate, externally is basically unstable, then the truss become a stable structure. If externally is unstable, the whole truss become unstable again.
Oh, okay, okay.
Yeah.
Can I ask another question about
Yes.
the beam one?
Yes. Yes.
For the previous lecture.
Okay.
Yeah, this one. For the first example for the solution part. Yeah, this one. For the first steps in calculating the moment. So the moment we assume the direction, or is there any rules to follow?
Okay, you mean this direction? Whether it is toward this side? Okay, no, you can assume any direction that you want. Doesn't matter. Doesn't matter. But the direction basically should be similar for M and M bar. Meaning if you assume it toward this direction positive, this one also should be the same.
So means the M and M bar must be the same direction.
Yes.
Last question. Do we have tests on the virtual method for the frames?
In the exam, you mean?
Yeah, in the exam, do we test the virtual method for frame?
Normally no, but I cannot 100% say that there's going to be any question coming from frame or not. As I said, if the number of elements in the frame are many, let's say you have one more frame element here, then your calculation is going to be too long. So that's why, since it takes time, normally we don't give any question from the frame structures. And frames normally in the exam are asked to be analyzed through moment distribution technique. So normally in the final exam, the first question normally is a frame that has to be analyzed through moment distribution. So it is highly unlikely that we give you a frame that to be analyzed through force method.
Oh, okay. Thank you, Doctor.
Okay, welcome. Any other questions?
Doctor, can you go back to this stability paper?
Yeah.
So in this case, when we have 2 rollers, it is because 2 is actually less than 3 reactions. But if we even have a third roller, it will still be unstable, right?
Yes, it will be unstable because we have geometric instability. This is what we call it, geometric instability. So it is not that always having 3 support reaction can give you a stability. You need to make sure that these support reactions are not parallel. If your support reaction are parallel, this is the time that your structure is still remain unstable. So for this case, you have one here, they are parallel. Even if you have another one or another one that are all parallel to each other, so still your structure is going to be unstable under horizontal force.
Yeah, doctor. Thank you.
Okay, welcome. Any other question?
Doctor, for the shear force diagram, we are going to draw the force for the external structure only, right? For example, before this slide, before this slide, yeah, this one, because you written the external force at point A is 30 tons. So at the shear force diagram should be 30, is it?
I don't know your question right now. What is exactly?
Because you written the 23.51 at the shear force diagram.
This one?
Yeah. How we get this 23.5?
Okay, this is the shear force and bending diagram for this structure. Okay, so we have a frame. We want to analyze this frame. This frame, in order to be analyzed, since it is indeterminate, we assume one of the support reactions to be redundant. Then we have 2 frames that is going to represent the real frame. So for each frame, we are going to calculate the bending moment from one span to another span so that we can get this delta C. So this 30 ton is the basically reaction force for the frame that doesn't have any horizontal support. But the shear force diagram that you see here is the shear force diagram of this structure that has the horizontal support.
So it means that we have to recalculate for the shear force at point A?
Yes.
Okay,
yes.
Okay, thank you, doctor.
Yes. After all this calculation that you see below these, all this calculation is to get delta C and delta CC. The moment that you got this one, it can allow you to calculate this XC. So when you got XC, then after that, you can go and draw the bending moment and shear force diagram for this structure, not these 2. These 2, we don't calculate any shear force. We just calculate the bending moments because we need them to calculate this delta. If you look at the equation, these bending moments are needed to be calculated so that we can get delta C and delta CC. But we don't do any calculation for shear force because shear force has nothing to do here in the calculation of delta C. So all this calculation that we do is to get this XC. The moment that we got XC, which is the redundant support reaction, then we can go and draw the bending moment and shear force diagram for the real structure. These are all representative of the real structure and has nothing to do with the shear force and all the things.
Okay, thank you, doctor.
Okay, welcome. Any other question? Please ask if you have any questions. It might be the question of your friends, so don't worry. There is no wrong question. Any question that you can ask can help others to also understand what we are doing here. Even if you haven't understood so far what we are doing, no problem. You just ask the question, we can explain here. Any question? Okay, so I assume that you have already understood what we have discussed. And we can go through our new basically title for this class, which is going to be this influence line. So let me share my slide. Okay, so we are here. Okay, if you had any question again regarding the force method, please watch the previous videos that I have uploaded. And then in our next class, we can start discussing them. Especially the question that raised by your student, by your classmate, you can also look at it during the time that you have free and see whether you also have the same problem in the calculations or not. Okay, another new topic that we are going to discuss in this class is about influence line. Why we need influence line? So consider a bridge that a lot of cars pass over it. Unlike the normal structures like the buildings, bridges are basically exposed to or subjected to moving loads. And these moving loads basically are very heavy, considered to be a heavy loads, because a truck may have around 40 ton, 50 ton mass moving over the bridge, and this is considered to be a very large force compared to the dead load of the bridge. So when it comes to moving load, the bending moment and shear force diagram that before this we learned about them to be used to calculate the worst basically case scenario is not functioning well anymore, because when you want to calculate the bending moment and shear force, we assume that the force is not moving and is constantly on the structure. So when you calculate the bending moment, you can always say that, okay, this is the place that gives me the maximum bending moment. But if you move, if your load is moving, that location that you have already assumed to be the maximum bending moment may not be valid anymore, because the moment that the load is moved, the location of maximum bending moment and shear force also is going to move. So in order to deal with this, we need to have another technique to help us to understand how bending moment and shear forces are changing when the load is moving over the bridge, for example. So influence line is not about bending moment and shear force. Even if you are going to see after this, you are going to see we do calculation of influence line for bending moment and shear force, but it is totally different from what we learned before this about bending moment and shear force. Let me just draw one beam for you to make it more clear. So if you have a beam with any loading on it, like the one that I have drawn here, so you can easily say to me that under this load, normally we have a bending moment diagram like this, and then this is going to be the maximum bending moment that can occur inside that beam. So if you have the bending moment, you can design the cross section easily. But the question is, what if this basically load is able to move? So if it can move, then our load, the bending moment is not going to look like the previous one. For example, the load can move to this side, and half of it is remaining on this span. So you cannot say, basically, this is my bending moment diagram anymore, and it's going to change. So the bending moment diagram and shear force is not helping us anymore to get the maximum, basically, reaction. And we need to have a new technique to see how bending moment changes when the force or the load is moving over the bridge. So this is what we are going to do in influence line. So the job of influence line is to tell us how support reactions, bending moment, shear force in one specific location. So this is very important to understand that we are drawing influence line for one specific location. It is not for the whole span. Meaning, I want to know that the bending moment, let's say at this point, how it changes when the load moves over the bridge. Or I want to know how the bending moment or shear force at this location is changes when the load is passing over the bridge. So when we are talking about influence line, we are talking about one specific location. We are not talking about the whole span. So that in that specific location, either we can calculate the shear force, how it varies, bending moment, how it varies, or even for support reaction, we can do the same. Meaning we are interested to know how this support reaction is changing when the load moves from left to right, or from right to left, or how this support reaction changes when the load is moving from left to right or right to left. So this is a very important point to differentiate between influence line and bending moment and shear force diagram. In influence line, we get a diagram that can say to us how shear force or bending moment changes in one specific location. So that location is arbitrary, meaning it's up to you. You want to see influence line in this location, this location, this location, or many other locations. It's up to you to select the location or select the support reaction that is of your interest. But the influence line is giving to you the change in the bending moment and shear force only for that specific location. However, when you draw a bending moment diagram for constant load, you get it for the whole span, not only in one location. So this is the important thing that you need to understand before we go through the influence lines calculation. Okay, now let's go and have a closer look to a beam that basically is going to be used to teach you what we mean by influence line. So in this beam, which has 6 meter span length, we want to see how support reaction at point A, that we refer to it as RA, changes when a unit load moves from point A to point B. So we are going to change the location of this point slowly from left to right. And when the load location changes, we are going to look into the support reaction value. So we have a unit load applied to point A, and then we want to see how much is RA. We move this load, let's say 0.6 meter away from point A. We look into the value of RA. We shift it again to another location. We look into the value of RA. So we do this until the load reaches to point B. So right now, our load has passed all over the span from point A to point B, and we have got the value of RA for any location that the load was there. If you draw a graph that shows the value of RA, considering the location of this force, you get influence line of RA. So if you look at this curve, when the load is at point A, the value of RA is 1. You can easily calculate this is 1. All the force comes to support reaction, and definitely RA equals to 1. When the load moves 0.6 meter to the right side, so we don't have the other loads, we have only one load applied here, and this is a time that if you calculate RA, we can easily calculate because this is a determinate beam. The value of RA is going to be 0.9. If the point is coming exactly to the middle of a span, meaning we have 1 kilonewton force in the middle of a span, the value of RA is going to be 0.5 because it is going to be distributed uniformly between point A and point B. So that's why in the middle of a span, you get 0.5. And then when the force reaches to point B, all the force transfers to support B, and RA becomes 0, as you can see here. So this curve basically is the one that we call it to be influence line of point of support reaction at point A. So this line shows to me that when the load is moving from A to B, how RA is changing. So you cannot say that this is a support reaction in any location. No, you're looking only at point A, a support reaction at point A, and you want to see when the force moves from point A to B, how this support reaction is changing. You can see the maximum occur when the load is exactly at point A, the minimum occur when the support reaction, when the load is reaching to support reaction at point B. And along the way, the load is decreasing, the load is constant, but the value of support reaction is decreasing. So this is how we can use this graph to design the support reaction at point A, because if you tell me when is the support reaction at point A maximum, when a moving load passes from A to B, I can tell you when the load is exactly at point A. When is the minimum support reaction at point A under this moving load? It will tell you when the support reaction or when the load comes to point B. At that location becomes 0. So you can see by looking at the graph, we can easily know that when the support reaction becomes maximum, when it becomes minimum. And along the way, when it passes over the bridge, how it changes its value. Similarly, you can draw another influence line, but this time for point B, meaning support reaction at point B. So again, you can put the load at different location and get how much is the reaction at point B. So when the point load is at, this unit load is point A, support reaction at point B is 0. When the load comes to middle of a span, then support reaction becomes 0.5. When the load comes exactly to point B, support reaction at point B become 1. And all support reaction is transferred to point. So if you connect these points to each other and draw the graph, you get the influence line of support reaction at point B. So you can see it is similar to point A, but with opposite basically changes. When support reaction at point B is 0, support reaction at point A is maximum. So it's very interesting to look at these two graphs, because it tells me when the load is moving from point A to B, how support reaction at point A and B are changing. When this one is maximum, this one is minimum. And when this one is maximum, this one is minimum. When this one is minimum, this one is maximum. And when the load is in the middle of a span, the value in both of the support reaction becomes similar, 0.5 and 0.5. So this is what we call it influence line for support reaction. I think in order to give you some rest, we can have 15 minutes of rest. Then we can come back to see how we can use the same technique to draw influence line for shear force and bending moment diagram. Okay, for bending moment in one specific location. Okay, so let's go and have a rest. I stop sharing. Then we can come back and continue. And I stop also recording. This way the video is not going to be too long.